Hello, good morning, good afternoon, and good evening. So welcome you again to this World Large River and Delta System Source to Sink webinar series. So today we invite Professor Jaap Nienhuis from School of Geoscience, Utrecht University. I believe the local way to see is Utrecht University. So before I introduce Jaap, so I would like to say our next webinar. Our next webinar, remember, starting from this week to December, we will have two seminars, two talks per week. So Wednesday and Friday. So same time, and occasionally some speak. If from the western coast of US, we may be a little bit delayed. So I will keep you updated. So Friday, Professor Uri Shatner from University of Haifa, Israel, will talk about the Nile River derived sediment, the longshore transport across the Eastern Mediterranean Sea. So please mark your calendar and come back this Friday, same time as today. So also, if you want to keep update, you can follow us on Twitter. So the Twitter account is Source2Sink. It's very simple, and you can be the number 800 follower if you do it now. So Source2Sink on Twitter. And at the same time, as you might know, all our presentation will be live streamed on the YouTube channel. So the YouTube channel address is tinyurl source2 So if you log in there, you can subscribe or follow. Then if we have update, you can immediately receive a notice. So all the previous presentation, wonderful talk have already been archived over there. You can go back, rewatch, and feel free to use for your class in your classroom for student, for your research. So this is the purpose of this webinar series. Thank you for your support. Okay, Professor Jaap Nienhuis, as you can see from his CV, he graduated from University of Twente, get a bachelor degree and a master degree, then got a PhD from MIT Woods Hole, the marine geology geophysical program in 2016. And then after that, a couple years postdoc, and now back to Utrecht University as an assistant professor. And so today, we are very happy to get him. He just published a paper about the global river and the delta systems in Nature. So, Jaap, now is your turn. Please unmute yourself and share a screen.
Okay, thank you, Paul. And thank you everyone for attending. Let me share my screen here. All right. Can you see it okay, Paul? All right. I'm going to talk about my river delta analysis, the global analysis that Paul was alluding to, and I'm trying to gonna try to put it in a source to sink perspective as well. I'd like to acknowledge the funding from National Science Foundation and the Dutch Science Foundation, and also the American Chemical Society. But mostly I want to thank my students for all the discussions and insights that they helped me with. Pani, of course, postdoc, Ahmed, John, and Derek. And of course, also all my collaborators and advisors over the years that I've listed here that contributed a lot to this work. A lot of people have asked me why a global analysis, what do you hope to learn from river deltas by studying so many? So first I'd like to go into that a little bit. And I think mostly the reason for us trying to expand river deltas and really studying basically all the ones we could find along Earth's coastlines, is that we can then really try to compare and contrast their morphologies and their morphodynamics. So of course, as you all know, if you look at a lot of different river deltas, all of their shapes and boundary conditions are going to vary dramatically, right? From the Ebro Delta here, wave dominated, to Arctic deltas, to kind of the classic river dominated Mississippi River Delta. And so by studying all of them, we're not just hoping to get a better sense of all of the river deltas that are out there, but also gain a better understanding in why the different processes make individual river deltas the way they are. So how different boundary conditions connect and make these river deltas different from one another. So in this talk, I'd like to start with predicting or using our global analysis to say something about delta morphology, so that the picture of the river deltas as they are today. And after that, I'd like to go into morphologic change a little bit, so how we might expect them to change into the future, or how they have changed over the past. And then lastly, I'm going to try to tie that into a source to sink. So delta morphology. One of the things I want to kind of start out with is thinking about a coastline without a delta. So the picture you see here, I drew a big black box over a delta that has formed there. But as you all know, that delta has formed there because a river has brought in sediments with a certain water discharge, sediment load, and grain size into that basin. Sediments that then were later reworked by waves and tides and sea level fluctuations. So predicting delta morphology, the way I see it, is really trying to use these boundary conditions to say something about the morphology that would end up resulting from those boundary conditions. And if we do that very, very well, I'm not sure if that's possible. If we do that very well, you might end up with something like this, right? The Mississippi Delta in this case. And even if we can't predict all of it, perhaps we can measure some attributes of this delta and predict those. And of course, one of the reasons we're doing this is that, well, let's say water discharge changes into the future, or waves, or sea level, would we then predict a different delta morphology to form, such as this one? And that would also then give us some insight in how these systems would change over time, a quantitative insight. Of course, I'm not the first one to think about this. We should all start thinking about others that have thought about this in the past, and most prominently, of course, Galloway in '75, who made this triangle that probably a lot of you know. But delta morphology was cast as resulting from three main drivers: a sediment input, a wave energy flux, and a tidal energy flux. This triangle has been extended later, of course, in thinking about how different grain sizes from gravel to more fine sediments would affect morphology as well. And this triangle has given us a lot of insight in the variation of delta morphology globally, but it's really hard to make that into a predictive framework. And that's because of that triangle, the axes are often undefined or a little vague. So for example, one of the earlier papers said that the fluvial dominance, or the fluvial input into that triangle, was governed by river water discharge, and the tidal energy, or the tidal component that drives delta morphology would be tidal energy flux in watts per meter. But in trying to apply this to this triangle, the problem, as you could probably see, is that we don't have a good sense of a delta morphology that would, for example, end up if you force a system with 100 cubic meters per second of water and 10 watts per meter of tides, right? We don't know what kind of morphology would end up resulting from that combination of fluvial input and tidal input. And our old deltas generated with that set of input conditions then going to be equal? Or is it some other variability, perhaps because of grain size? And so that's really what's giving us the motivation to try to cast this triangle into a more quantitative framework. And we started out doing that. It was actually part of my PhD thesis that I worked on with Andrew Ashton and Livio Giosan. Really started thinking about the wave to river dominance first of that triangle. So really going from that river dominance here along this edge towards wave dominance. And again, thinking about a delta, but then drawing a big black box over that delta. If you do that, for example, this is a schematic where I've done that, where you force a coastline with some sort of sediment supply, and you know that waves are acting in the basin that would adjust that morphology. We're of course not the first one to think about this, and if you look at other studies, what they found for deltas governed in various ways by waves, this classic cuspate shape is often what you find, where a sediment supply would come in, waves would pick up that sediment, move it along shore via alongshore sediment transport, and you get this cuspate delta prograding forward. I found this paper, by the way, by Komar, and had this caption. I thought it was funny, where back in '73, it cost $45 to generate this simulation. I'm very happy we're a couple of decades ahead now. But one of the insights that Komar had, and that other people have had as well, is that really the physical mechanism making wave-dominated deltas was sediment input into the river mouth, and then moving that away from waves along both sides. If you then take that one step further and say, well, what is the actual shape of that cuspate shape? How pointy is that shape going to be? You can think about how waves move sediment along shore, and this is the paper by Andrew Ashton and Brad Murray, where this graph shows how much sediment you expect waves to move away from the coastline. You can see that it depends very strongly on the relative wave angle. So if you have a certain amount of sediment input into the coastline, you can then find the angle that the coastline has to make for waves to move that sediment away. All right, if you have not very large sediment input, you're going to have a very small relative wave angle is going to be sufficient. So you're going to have a pretty flat coastline still. And you can use that then, that knowledge about waves and how they move sediment, to actually predict the angle that the delta would have in equilibrium. And you can make that prediction, and you can then test that prediction by moving this black box away and looking at the delta that formed. And that's what we did for a bunch of deltas on Java, and we found that that prediction is actually fairly decent. So what we found is that from increasing sediment flux, the resulting steady state delta is going to be pointier and pointier. Of course, because of this prediction, you can also find that if you would then increase the sediment flux for this particular delta, you need a pointier delta to get back into that steady state. So waves are then more efficient and move sediment away from the coastline again. On the other hand, if you have higher wave energy, you don't need as much of a cuspate shape. You only need a very small angle to move that away. So waves act in the exact opposite fashion that the river does. Lastly, what you saw is that this graph here, of course, has a maximum at around 45 degrees. So the other prediction is that if you put in more fluvial sediment flux than what then the maximum of this graph, so the maximum that waves can move away, the prediction is a river-dominated delta. And that's also what we found here again, looking at these deltas on Java. So for a certain amount of fluvial sediment flux, we don't find any angle anymore, but instead a river-dominated morphology. You can then cast this into two main sediment transport quantities. One is, of course, the amount the river brought in, and the other one is the maximum potential amount that waves can move away. And that ratio then it predicts when a delta would be river dominated. And if waves are higher, it predicts the angle of the coastline. Again, you can do this not just for deltas on Java, but for deltas anywhere. And you find that indeed for the Senegal, it's a very flat coastline. So it's one of basically the most wave dominated a delta can be. The Sao Francisco, you see a little pointiness in there. And then exceeding one, you get into a realm where you have things like the Tinajones, which is a special case I won't discuss, or the Mississippi River Delta, which is of course river dominated. The important thing is that this is a predictive ratio, so you don't need to look at the delta morphology to calculate it. One of the things I wanted to discuss, Weilun Gao just published a fantastic paper trying to extend beyond just a simple pointiness looking at wave dominated deltas, but instead found a lot of other feedbacks as well. One in particular where a river doesn't always need to prograde straight into the coast, but can also have certain angles. And he then found that those angles can then feed back into other things like river revulsions further upstream. So definitely check out that paper in Water Resources Research. But just to continue on more broad scale effects, broad scale morphologies of river deltas, the next step, of course, was looking at what tides do to delta morphology. And I think these contrasting the Fly and the Mississippi makes one thing very obvious. Of course, the Mississippi doesn't have much tidal action, and the Fly River has a lot of tidal action. And one thing you see is that if you look at the river width going from upstream all the way to the mouth, for the Mississippi, it stays more or less constant going upstream. And the Fly, on the other hand, starts out to be much narrower than the Mississippi, but towards the mouth becomes much and much wider. And of course, this is because of tides, right? There is not much tidal action in the Mississippi, so the mouth doesn't need to be much wider to accommodate those tides. But the Fly River, the mouth needs to be a lot wider because there's so much tidal discharge going back and forth. And you can make this quantitative by looking at models that people have made on tidal channels. And they found, for example, this paper found that there's a relationship between the cross-sectional area of a channel and the amount of tidal prism it can convey. And that it's kind of a constituent relationship between those two effects. And they allow you to then calculate ahead of time what cross-sectional area of a channel you expect because of a certain amount of tidal action. And in a paper I published with Ton Hoytink and Ton Tornquist, we converted that predictor into one that also takes into account some flow from upstream. So really studying an estuary in this case, or tide-dominated delta. And what it allowed us to do is predict the width of the river mouth depending on certain a priori parameters such as the upstream width or the tidal amplitude and other factors on the coastline. And if you know the width of the mouth and certain tidal angular velocity, you can then also predict the amount of water discharge going back and forth. And similarly to that wave question, we then simply converted the tidal discharge over the river discharge and say, well, if there is more discharge at the mouth going back and forth because of tides, and so you really have reversing flows, then you're a tide-dominated delta. And if you don't have reversing flows at the mouth, then you remain a river or a wave-dominated delta. So in this case, Ebro and the Mississippi are river or wave-dominated, and exceeding one, you get into a realm where the width is much wider. So that's the morphologic prediction in this case, and you're therefore tide-dominated. On the extreme end, you don't have any fluvial or water discharge, so you're like the Thames or simply a tidal channel with no upstream river. So putting these three fluxes together, we can recast this Galloway triangle and make it into a non-dimensional framework. So because all of these fluxes, of course, have the same dimension, so we could divide them amongst each other. And we can also make a morphologic prediction depending on where you are in this triangle. And that morphologic prediction, it doesn't include all morphologic elements, of course, of a river delta, but it predicts the protrusion angle and it predicts the amount of channel widening. And you can also look at it in kind of a sediment balance across the river mouth. We have a certain amount of fluvial sediment going in, a certain amount of sediments moved back and forth by tides, and some sediments moved away from the river mouth by waves. So having these predictions for delta morphology on a global scale based on boundary conditions then allows us to really extend that and predict delta morphology for all deltas where we have boundary conditions available. So based on global data sets, you can do it very easily across the globe. We use NOAA WaveWatch 3, which simply gives us wave energy parameters, wave height, wave period along the world's coastlines. The same for tides. We need tidal amplitude and angular frequency. We can get that from global models, such as this ASU Topax model. And then river sediment flux is slightly more uncertain, but there are global models such as the WMSED developed by Sagi Cohen, James Savitsky, and Albert Kettners, and others that provide a sediment yield on a gridded basis globally. So for all elements, for all the coastlines, we know the amount of sediment put in through the rivers. And then with some other algorithms, primarily based on hydrosheds data, we can then predict where all river mouths or all deltas would be, where there are enough sediments to create a morphologic delta. And we get to about 10,000 different river deltas. And then we can simply click a button and then predict what we expect the morphologies to be for all of these systems. This paper with these predictions we published in Nature of January this year. And if you're interested, all the data is available on GitHub here through this link. Of course, there's a lot of things you can learn from this data set. The first is simply counting the number of different delta morphologies. If you look at these end members, you quickly find that most deltas are very small and wave dominated. And if you look at the global discharge flowing through deltas, then most river discharge flows through tide-dominated deltas and river-dominated deltas. And also most sediments generated across the globe flow towards the ocean through tide and river-dominated deltas. As I said, the data is freely available online, so there's a KML file. You can get these different parameters and other parameters based on different rivers. And they also made an Earth Engine app with the address here. You can click on different drainage basins and then get aspects and data for individual deltas, and also for all deltas together, including things like land area change that I'll discuss later. Of course, aside from just plotting where we expect certain end members to be, we can cast all of these morphologic predictions back in that Galloway triangle and then you end up with something like this. So the size of the marker here represents the amount of fluvial sediment flux, so proxy for the size of the delta. And you quickly see what I said before is that most wave-dominated deltas are going to be very small, and larger deltas are either going to be river-dominated or tide-dominated. And they can be tide-dominated because a lot of these large systems tend to be very low sloping, and so they're conducive to a lot of tidal discharge. Think of the Amazon or Ganges Brahmaputra, for example. Other very important things you can do first, of course, is testing the model. So as I said, these are all morphologic predictions. So you can go across the globe, measure the amount of channel widening, measure the pointiness, or measure the overall morphology, and then have a predicted observed diagram and say, well, what is the accuracy of my prediction? Or how can I make it more accurate by introducing other empirical factors, for example? You see, it's reasonably accurate up to about 85% in total. As I said before, we're only predicting really the amount of channel widening or protrusion from the coastline in case of wave to river dominance. But there are other empirical predictions that you can basically hang up and put into this triangle and see, well, other things that co-vary with wave and tide and river fluxes that we can put in this triangle and then also predict. So what I'm showing here is for a couple deltas, I measured the amount of distributary channels, ranging from 1 to more than 4, of course, and for the Mississippi or for the Niger Delta, for example. What you see here, if you look at the colors, is kind of an interesting divide between this lower half of the triangle and this upper half of the triangle. What that corresponds to is where wave-dominated sediment transport is bigger than either river, is bigger than the river fluvial sediment flux. So if with the wave sediment flux is larger, apparently they can effectively eliminate the number of distributary channels. So next I wanted to discuss morphologic change. So using this framework as I discussed before and thinking about how deltas might change into the future or have changed in the past. And we're going to use that same framework. So predicting delta morphology, and then thinking about these boundary conditions again, like water discharge or waves or tides, things that are not affected by delta morphology itself. And if you expect any of these boundary conditions to vary, then from that framework I introduced before, you would then also expect the delta morphology itself to change. So morphologic change of the delta. If this is, for example, a prediction of modern delta morphology or delta morphology in the past, you can then go, for example, to the Nile and say, well, the amount of fluvial sediment flux to the Nile has decreased drastically, as we'll probably hear on Friday as well, and because of the construction of the Aswan Dam in the 60s. So you see that the dam resulted in a very drastic decrease in peak water discharge flow, so also in sediment transport capability towards the mouth. And what we expect looking at this triangle is that if the river sediment flux decreases a lot and the waves stay constant, then you would expect a big decrease in the protrusion angle of your wave-dominated delta as well. And we can test that prediction by looking at recent change of the Nile Delta. And that's indeed something we see. So there's been a lot of coastal erosion. This is the Rosetta mouth, so one of the two mouths of the Nile. There's been a lot of coastal erosion focused very close to the river mouth. And you see kind of a diffusive change or slight shoreline progradation here as well, something we expect if the coastline diffuses and becomes less protruded. The same kind of analysis you can do on the other side of the triangle by looking at tide-dominated deltas or river-dominated deltas that will become more tide-dominated into the future. So one example of that is the Colorado Delta on the US-Mexican boundary. As you probably know, the water discharge to the Colorado Delta has decreased a lot over the years. So you would expect tides to become relatively more important for the Colorado Delta. And our prediction in this case for tide-dominated deltas is that because a delta becomes more tide-dominated, the relative increase of your channel width should increase towards the river mouth, but your fluvial, your river channel width should decrease. So there should actually be some infilling into the delta because of tides. That's afterwards. I wanted to show you this video, and that's actually something you can see here in the Colorado Delta. So there's been some infilling because of increased tidal import into the delta, and that's resulting from a decrease in water discharge and river sediment flux into the delta. You can do this on a global scale as well if you know how humans have altered fluvial sediment flux globally. We use a WM-SED, is that sediment model, to estimate that. So we have a prediction for pre-human influence sediment flux and post-human influence sediment flux, so the modern. And that's what I show on this map here. So for all the different deltas, the blues are where humans have reduced the fluvial sediment flux by 100% in a lot of the cases because of river damming. And the reds is where the model predicts a big increase in fluvial sediment flux because of land clearing mostly and deforestation. So for all of these systems, you can then predict how deltas would change. And then simply add that to this triangle. And that's what you see here. So all of these arrows represent an expected morphologic change because of human influences on the fluvial sediment supply. And you can see a lot of big red arrows pointing down. So those are the dam constructions I talked about before. Importantly, as I said before, these are changes to the boundary conditions. So these are changes to things affecting delta morphology, but they don't necessarily imply that delta morphology changes at the same time or at the same rate as that these boundary conditions change. So even though for this delta, for example, we expect a big decrease in the protrusion angle because of changes in boundary condition, that change in protrusion angle can take a long time. So even though boundary conditions might fluctuate very quickly, the delta morphology might lag, and the delta might have still ongoing morphologic change because of that change in boundary conditions. And of course, boundary conditions have changed into the modern, but they're also likely to change into the future. So I'm currently working with Francis Dunn here at Utrecht University as well to see how deltas might change because of planned dams or climate change beyond what I'm showing you here. And again, we can predict things like a protrusion angle or delta channel widening, but using empirical predictions such as the number of distributary channels, we can then also say, well, if a river delta is going from this side of the triangle to this side of the triangle, looking at other deltas, we then also predict that the amount of distributary channels is likely going to change as well. Of course, keeping the relevant timescales of such morphologic change in mind. So last thing I wanted to talk about a little bit is trying to cast all of this into some sort of global source to sink framework, especially because of course, this seminar series. And one of the things I thought would be nice to think about is kind of a feedback between source to sink and delta morphology. So of course, we all know in this source to sink framework, deltas occupy a very important part of that. And aspects of this source to sink, primarily, of course, the amount of sediments feeding into deltas is going to have a great impact on delta morphology. But at the same time, this feedback extends back as well, in that the delta morphology can have an impact on delta source to sink, right? By changing, for example, how quickly sediments are moved through the delta, or how much sediments are taking up and contribute to delta land area versus the type or amount of sediments released to the deeper ocean. So there's this feedback that I think would be neat to consider. One of the things we can do with this global data set is simply say, well, what's the big, what are some of the big numbers in terms of source and sink? Well, for the modern, for example, we know that on a global scale, rivers carry about 9 × 10⁹ cubic meters per year of fluvial sediment through all of the deltas together, not counting Greenland, as we learned last week. And that all of these deltas globally, if you look at Landsat images, something I haven't really gone into today, all these deltas globally over the past 30 years have gained about 50 square kilometers per year of land. So thinking about how efficient deltas are in using that sediment that is feeding them and turning that into deltaic land, we find that there's an effective sediment deposition depth of about 180 meters. So deltas currently, if you look at these two numbers, need about 180 cubic meters of sediment for every square meter of delta land that formed over the past 30 years. You can take this a little bit further back in time and say, well, we know that there's a global delta area of about 900,000 square kilometers. We know that the average delta age, approximately, the delta started growing when Holocene sea level rise slowed down. So on average, deltas are 7,000 years, 6,000 years old. So on long-term growth rate, we expect it to be slightly higher actually than what we've observed in the past 30 years, is about 125 square kilometers per year. And also on this very long term, given that we actually don't know much about global sediment fluxes over that time period, but assuming the same as the last 30 years, we expect deltas historically over the Holocene to have been slightly more efficient in generating new land. So about an effective depth of about 100 meters of sediment deposition. These are, of course, very rough numbers. And as you can hear, this is something that we haven't really worked out yet and are working on now with some people. But you can ask very interesting questions like, how does that efficiency then depend on or vary between different delta types? Or wave or tide-dominated deltas going to be more important than other types of more important or more efficient in terms of land building than other types of deltas? Does that land building efficiency depend on fluvial sediment supply, depend on sea level rise? And of course, are all sediment used for land building? Is it just a coarser sediment on this global scale that has been very important for land building? And are a fraction of all the fines retained or flushed out to sea? And what can we learn by looking at all of these deltas together? This is something we haven't published yet, so I'm currently still working on this. One of the things we can do is kind of make cross sections of all deltas. So this is along channel distance and elevation. So these are delta cross sections of the Rhine, for example. The Eel, of course, is a lot steeper. And then using of all 10,000 deltas, these cross sections, we can then apply a framework such as the one I'm showing you here, where we say that the delta has formed over this kind of basement slope, and the efficiency with which deltas form land is basically the amount of sediment they're allowed to trap in this triangle here. And because of observations of what deltas have done in recent years, we can then verify that by looking at the amount of land gain or land loss. We can plug this into in a model and then generate figures like this, where I think this needs some explanation, and where I plot the fluvial sediment supply feeding the delta, and on the y-axis here is an effective sediment retention. So using this model, we then looked at how much of the sediment feeding the delta was needed to actually contribute to the land gain we observed in Landsat images. And so if this is below 1, then some of the sediment is lost and is not add to this deltaic wedge, so to say. And if this is above 1, then magically new sediment appeared. So this could be organic production, for example, that added to delta volume that was not represented in the fluvial sediment flux. One of the things you see here is that because you divide to very uncertain numbers, there's going to be a lot of scatter. One of the advantages, on the other hand, is that because we have 10,000 deltas, you can then do statistics on average deltas behavior, for example, looking at this fluvial sediment supply. And one of the things you see here is, if you do that, if you look at bin statistics, is that the bigger the delta becomes, the less efficient it becomes in retaining the sediment that was fed to them. Going from about 1 on average to about 10% or 20% for the much bigger systems. But again, this is very, very crude data, so use it with caution. The other thing you can do, of course, you can look at other parameters such as relative sea level rise and saying, are deltas that are experiencing higher amount of relative sea level rise going to be more efficient in capturing the sediment that was fed to them? And yes, that's something you see as well. So for very low amounts of relative sea level rise or even uplift, you see that not much of the sediment was retained, but if you go to higher amounts of relative sea level rise, more of the delta, more of the sediment was retained on the delta top and in the delta front. But of course, as I said before, this is very, very crude data. So this is just a primer. So to conclude, first, we have kind of a new general delta theory in terms of providing quantitative predictions on delta morphology that we can apply globally. Second is we can use theoretical and empirical predictions to say something about how deltas have changed or will change into the future. And lastly, we're thinking about extending this to say something about deltas as they exist within source and sink. So thank you very much, and thanks to all my collaborators and students mostly.
Thank you, Jaap. I think this is a wonderful talk. So we have a couple of questions in the chat room. You also can, Jaap, you can click the chat room. And
okay.
If anybody want to ask a question, you can unmute yourself. You can click the participants and raise your hand and unmute yourself. But here, let's answer the two questions here. The first from Billman. What does your model predict for typhoon, hurricane, or tsunami, that kind of event?
To be honest, not very much. So the mostly the alongshore sediment transport, so the wave element in how waves change delta morphology is through alongshore sediment transport, and alongshore, and that's something that happens on kind of very long time scale, so to say. I'm not sure if I'm saying this correctly. But the important parameter of waves here, in this case, shaping delta morphology, is alongshore sediment transport. And that's mostly determined by very long-term wave statistics. So not taking into, so the effect of storms in that case, in my framework, doesn't have, storms don't have a big impact on delta morphology in that framework.
Very, very good.
But importantly, it's, I think, important to note that if they would have a big impact, then you would expect the delta morphology, so a very large scale, also to be affected by individual storms. And that's something, of course, we don't really see, right? The Mississippi Delta large scale morphology is not affected by an individual hurricane or storm.
Okay, the next question from Uri Shatner and the Haifa. He asked, can you estimate the volume of sediment the delta are losing to the longshore transport? The delta, what we talk about is mainly the proximal depot center. But as we mentioned, there's also a big portion, the longshore. So in your work, can you estimate how much left, how much stay?
Not really either. So in our model, as you saw in that, where that cuspate delta shape was formed by competition between what the river put in and what the waves were able to move along shore, that is all retained within the volume of the delta. So there's basically an infinitely straight alongshore beach on both sides. And if there was asymmetry in the wave climate, then whatever was lost on the downdrift side is then gained by the delta on the updrift side. So that the alongshore sediment transport doesn't do anything to the delta volume in a net sense in our model.
Okay. I think the both above two questions, we need some PhD student work on it. And yes. Okay, the next question, the Michael Stickler. So, because he asked, presumably in a large delta, much of the sediment must build the pro-delta, subaqueous delta, and the cloud to support the land, the subaerial portion. So the river should be kind of a low ratio. Would you agree?
Yes, I think so too. So that number of like an effective depth of 180 or 100 meters, that of course is also like a shallow to average depth of a continental shelf. So I think there's definitely a connection between those two.
And also, Jaap, also have a question, because most of the delta we all know begin to form mainly middle Holocene 7,000 years when the sea level high stand. So in the beginning, early phase, because the river, the channel coming to a narrow estuary or channel or valley. So the sediment, the retention rate should be much higher than today. Because if you look at it today, even there's no sediment reduction, most of those large delta, the progradation is very limited because it entered to an open ocean, open shelf. So most of the sediment may escape to the shelf or even through the canyon to the deep sea. And the retention portion left to build the subaerial portion may be less and less. So
I completely agree.
Communicate that so far, right?
I completely agree. So actually, postdoc Derek Vaughan is working on exactly that. So that the efficiency of deltas if they sit in their incised valley, of course, you expect them to be much more efficient in generating land than when they're out on the shelf, like the Mississippi or other deltas.
Yeah.
So, yes. So land generation 6,000 years ago was probably a lot more efficient than it is today.
Yes, and many delta is kind of like a mature, but still some still developing, but some already open ocean, like the Irrawaddy.
Yes.
Like the Yangtze even. So this is just a kind of, okay, the next question, let's see, from Irina. So Irina is that, can you also read, I wondered about the relative trapping with the sea level rise. If you would cluster the data into deltas with the loss of distributaries, dense network was clustered with the field distributary channels, would you find the different trend?
That's a great idea. I have not tried that, as you can hear. But yeah, yes, one of the like the really big downsides of doing this kind of cross-sectional area approach is that you assume that the whole delta behaves as one, as basically the sediment is effectively spread along the entire width of the delta, the fluvial sediment. Yeah. And that's not the case in reality. So that's a great thing to try. We'll certainly think about that.
Yeah, we have some questions from Jim Best and Stu Kiel. And you too, if you like, you can unmute yourself, directly ask, because that could be more interactive.
Yeah. Hello, Paul. May I ask a question? This is Wei Jun.
Wei Jun, can you hold a little bit, because there's two more questions in the waiting here.
Okay.
So Jim's best. Okay. Jim, do you want to talk?
Yeah, thanks, Paul. Thanks, Jaap, for a great talk. My question, thinking about the old classification, looking at delta front processes in terms of the density difference between incoming river and basinal fluid density. What I was wondering, do you see any change in growth rate or delta morphology for different density ratios between what's coming in and the basinal fluid density?
A good question. No, I have not looked at that, and that's primarily contrasting Arctic versus other oceans, or also like freshwater lakes, for example, or.
Well, I was thinking if you had something that was higher density that then formed a hyperpycnal flow, then presumably that sediment flux won't reflect in any growth in delta area. So I'm wondering whether, especially around, big river deltas where you may have, not such saline water nearer the shore, whether that's going to give any complications to the growth rate depending upon the density ratio rather than just the flux.
That's a great idea. That's something I have not thought about at all. I know that John Warwick has some interesting ideas about how efficient deltas along the west coast are in terms of keeping sediment within their littoral cells. But I've not kind of tried to expand that to other deltas elsewhere. Okay, that's a great idea.
Okay, thanks, Jaap, for a great talk. It's really interesting.
Steve, go ahead. Steve.
Thanks, Jaap, for a great talk. I guess I'm interested. I was always been interested in the fact that you've got many of the world's large rivers entering very energetic tidal regions, and those are also areas where you have large subaqueous deltas offshore. So I guess I'm wondering have you thought about trying to look at the buffering effect of this sediment reservoir in these large subaqueous deltas in the face of increased damming and reduction of fluvial and sediment fluxes from rivers?
So in terms of the buffering effect, it's what you mean is like picking up sediment from the subaqueous delta and moving it onshore I know that's kind of what we hypothesized when we found that when tide-dominated deltas are faced with reducing sediment fluxes, we don't see a big change in land area actually. So wave-dominated deltas that are being dammed erode much faster than tide-dominated deltas. So that's definitely something that we're hypothesizing, but we haven't tested that on this scale yet.
Wonderful. So
yes.
My question is, Wei Jun, this is exactly the purpose of this webinar series. We can stimulate all that kind of idea globally. Okay, so Wei-Jun, go ahead.
Is my microphone muted or you can hear
Oh,
me?
yeah, we can hear you.
Okay, so a great talk. My question is maybe a little beyond what you talked. So in many of the large river system, deltaic areas such as Mississippi and Yangtze, we have the strong eutrophication and hypoxia. And in recent decade, some of them are stabilized the river nutrient supply. However, the hypoxia eutrophication seems keep growing. And one reason I listened to your talk, I wonder if it's because of decline in sediment supply, which tips the coastal ecosystem balance further to eutrophication. I would like to hear your thoughts.
It's a great hypothesis, and I have no comments in whether that is feasible or not. I typically try to stay away from chemistry as much as I can.
Okay, understandable.
But
that
no,
sounds like
I'm very happy to work with you and see if we can test that thought. And all the data is online as well, so feel free to check that out too.
Thank you.
I somehow kind of agree with what the Professor Wei-Jun just, the question he asked you, because based on all the data we collected, particularly those large river systems, even 80 to 90% sediment reduction, but the eutrophication, the hypothesis still kind of growing, because now we are kind of suspected. We don't know because we need more research, particularly from those biogeochemical community. So how the suspended sediment play a role in eutrophication? If we have very turbid water, that clay absorption, flocculation, or physical remove that proteins or nutrient could be higher. But now if you filter all the sediment by the dam, that same kind of nutrient, same kind of protein dumped to the coastal water could be magnified, enhance the rate of primary production or eutrophication. I don't know, I'm a geologist, but I just maybe a totally nonsense, but we need to work on this. So
Paul, is there someone ahead of me? This is Tom.
Oh, Tom, go ahead, yes.
Yeah, nice talk, Jaap. I just wanted to mention, I guess, sort of along the lines of what Paul and Wei-Jun are talking about, not to keep dragging you into chemistry, but I'm wondering if some of this relationship with respect to eutrophication might be related to another factor that's happening at the coast, and that is sort of the instability of the marshes and mangroves that are associated with these delta systems. So, when you think about the efficiency of how these deltas built early on relative to now, and you think about sort of the impact of new material, water and particles arriving to the coast, how do you, what are your thoughts about not so much the eutrophication and so on, but what are your thoughts about the efficiency of retention relative to the stress that's being put on coastal marshes and mangroves that help to retain particles that are being now challenged by inundation and sea level rise? So that balance of sort of the vegetation component of what holds the delta together is being challenged more, perhaps, in these times. And how does that factor into some of the predictions? I don't know if you understand. Hopefully that was clear enough.
Yeah. Are you talking about the human influence on like delta morphology or?
Yes, and also just the stress that's been put on different systems by human cuts that have been made through systems and other factors that are impacting the vegetation that fits into sort of the model of what stays and what leaves a delta region. Without getting into all the details, let's just call it global change on vegetation associated with deltas, vascular plant vegetation?
Yeah, it's a great question. I know, like, we're from like a sedimentological point of view, we're really interested in how humans have shaped these systems and basically have made it much harder for sediment to be incorporated onto the delta plane and much easier to be flushed out to the open sea. So that's something we're working on right now. Because of course, a lot of the analysis I've been talking about really assumes that the delta is able to move about freely. So there are no levees, there is nothing like dredging going on that would maintain a channel in place. And so the current thinking of me, and I think a lot of others as well, is that humans have really made it much easier for sediments to escape to the open ocean, and that's also have kept it from being trapped by vegetation. But I don't know of any quantitative studies, especially. I don't think anything on this scale has been done looking at that.
Okay, that's wonderful. We have some more discussion in the chat room. I think maybe one day we should host just a discussion or panel discussion, about the source to think. Thank you, Jaap, for this wonderful talk. And before I go, yeah, I would like to see this talk and the previous talk all recorded on the YouTube. Today, this presentation we broadcasted by 3 platforms. On the Zoom, there's 55 people. On the YouTube, there's also more than 50 people. And also the Chinese Tencent meeting, also around more than 50 people. So at least more than 150 people participate this live presentation. But many people go back, I know, like a western coast of US, like our colleague in Australia, or they are too late or too early. So they will come back to watch this presentation on the YouTube. So it's a YouTube channel again. So Friday, come back, we have another wonderful talk about the Nile River system, the longshore transport. That's a beautifully large river, longshore drift, active margin. So, and again, as I mentioned, if you know somebody, any colleague who can talk about the high latitude river system, like the Yukon River, the Mackenzie River, and particularly the Russia River system, the Oberyersee and the Lena, and or even Colorado in US, Magdalena, Orinoco, and Congo and Niger, please let me know. We try to build that webinar series more useful for students who are interested in the land and the river system. Okay, let's see if we know any other question. So we will stop here, and please coming back Friday, and of course next week. So, okay, so long. I see you Friday and also next week.